Modern ecosystem destruction is outpacing our capacity to repair it by millions of acres every year. To prevent total biome collapse, we require an immediate surge in the speed of replanting operations. Traditional reforestation relies on a linear, manual process. Human crews walk a grid, stop at viable soil, dig a hole, and drop a seed. This chart compares deforestation against replanting capabilities. The steep exponential curve of forest loss rapidly pulls away from the flat linear trajectory of human labor. That widening gap represents a logistical deficit. Destruction accelerates while restoration remains limited by the physical speed of human workers. Simply adding more labor to a traditional forestry model does not solve the underlying problem. It only marginally increases the slope of the restoration line without changing its linear nature. To bridge this gap, we need to move toward a system capable of exponential scale. While the biology of germination remains complex, the primary bottleneck for global restoration has become a problem of logistics and mechanical engineering. The solution to this deficit lies in algorithmic forestry. This model utilizes a decentralized, autonomous drone swarm. By removing manual planting, we deploy networks of hardware to map and reseed burned ecosystems simultaneously. Building this system requires three technical pillars. First, edge compute hardware, custom neural networks, and kinetic ballistics. Standard drones are observational. They record data for later analysis. This system requires a drone to perceive a target and take physical action in real time. To understand how this works, we will deconstruct the system from the hardware constraints of a single unit up to the deployment of a macro swarm. By coupling classification software with physical ballistics, we move from observing a burned landscape to actively replanting it. Autonomous flight in a burned environment requires real-time spatial mapping of highly unpredictable, chaotic terrain. The drone generates a 3D topographic map to calculate obstacle-free flight vectors through falling branches and dense ash columns. Standard AI processing uses a cloud compute loop, sending data to a distant server and back. This latency is represented by this expanding red timer. At high speeds, this delay is fatal. The drone will collide with debris before receiving instructions to adjust. To solve this, the processing must happen on the drone itself, a method known as edge computing. By housing the inference chip directly on the drone's chassis, we eliminate the need for a distant server. This reduces the processing delay from several seconds to single-digit milliseconds. For autonomous forestry, computational proximity to the sensor is the primary determinant of system survival. Once the hardware can process data fast enough to fly, it must then solve the software identification challenge. This task is handled by a custom convolutional neural network, or CNN, running on the onboard edge hardware. Wildfire zones are visually chaotic. The camera feed is a mess of gray ash, charred wood, and small hidden pockets of topsoil. The CNN pipeline pushes the camera feed through digital filters, stripping away visual noise based on spectral reflectance. Next, it analyzes geometric data to differentiate jagged charred wood from smooth, nutrient-dense soil, outputting digital bounding boxes around high-probability topsoil patches. Running this classification continuously at operational flight velocities requires immense computational efficiency. The value of the CNN lies in its ability to filter chaotic ecological noise into actionable targets in real time. The system must now translate that digital bounding box into a physical event through a perception-action loop. This physical event is executed instantly by a pneumatic seed-firing ballistic system mounted securely to the drone's underside. To hit a target from a moving platform, the edge processor calculates the ballistic trajectory by integrating drone velocity, altitude, and crosswind resistance. As the drone approaches the target, the software updates the firing solution every few microseconds. A precise synchronization sequence triggers the pneumatic payload at the exact moment the trajectory aligns with the viable soil patch. We maintain strict physical tolerances to ensure the capsule hits with enough force to embed at the correct depth, without shattering on impact. Mastering this ballistic integration bridges the gap between software classification and tangible ecological engineering. Moving from a single unit to a macro deployment requires a swarm architecture. We use decentralized swarm logic, which removes the need for a central command server. This eliminates single points of failure and reduces the communication load. On this map, multiple drone nodes radiate outward. Using a peer-to-peer data protocol, they share boundaries in real time to prevent redundant planting. These expanding polygons scale exponentially, while the human crew remains locked into a slow, linear path. This model is inherently fault-tolerant. If one drone fails, the surrounding nodes automatically recalibrate their boundaries to cover the gap. This architecture provides extreme scalability with a minimal marginal cost per acre. Manual planting systems cannot match the current pace of global destruction. By integrating edge compute optimization with kinetic ballistics, the Silvan circuit enables autonomous ecosystem regeneration at the scale required to counter modern environmental loss.